It's Susanna. I am one of the fellows of the RAIS project and as such a PhD student at KTH, Royal Institute of Technology in Stockholm, Sweden. In this video webinar, I would like to give an introduction to the tools we can use to identify, for example, the most influential user in a social network or the most reliable website on the web. To do this, we are going to answer the two questions that you see here. First, we'll get started with the basics on top of which the tools we are going to look at are built, and then we are going to go through how these tools are actually applied to find the center of the world, if you may. But first, we need to go back to the Königsberg of the mid-17th century. The map you see here show what the city looked like back then, and one of the first things that you may notice is that there's a river passing through, and of course a few bridges connected in different parts of the city. At a certain point, someone asked, is it possible to cross all 7 bridges once and only once? So let's go back to the map and see if we can answer right away. Some may say that maybe. However, there's a lot going on. There's a lot of information that we don't really need, and it's even confusing because it's going to take you a while to figure out where the 7 bridges are. So let's remove this extra information and keep only the bare bones. What we end up with is something like you see here on the right. The underlying map is not necessary, but I put it there just not to get lost. And what we did here is basically map each riverbank or island to a circle. And we have A, B, C, and D, and map each bridge to a line connecting two circles that we will call links. So this structure made of circles, which from now on which we will call nodes and links or edges, is known as a graph or a network. And it contains the information we need to figure out that the answer is no, we cannot cross all the bridges once and only once. And this problem of the 7 bridges of Königsberg is famous because some say it started the graph theory as we know it today. But the reason why I showed it to you is to understand what graphs are, how they, what they represent, and how we can model a phenomena with one of them. Then, why do we need graphs? What can we do with them? The reason why graphs are a very cool thing to work with is that we can learn something about the entities the nodes represent by looking at the way they are connected to each other via the links. And this is exactly what we are going to do now. One of the first numbers that we can come up with to capture the structural properties of the connections in a graph is the degree of a node. It is defined as the number of links touching our node, and as a result, it's also equal to the number of neighbors this node has, that is, the nodes that it is directly connected to. The degree as a feature is pretty easy to compute, but at the same time it's very significant, and as a matter of fact, in many cases is going to be broader enough to, for example, identify the influencers in a community. But the degree does not capture everything. Another tool we have is a family of features that assess the importance of a node in a graph. And first and foremost, among these, we have the measures of node centrality. There are many versions of this concept, and here I listed just 3 of them. First, we have the eigenvector centrality, which it captures not only the number of links touching a node, but also the importance of the node that is at the other end of these links. And you can think of it as a number that gets assigned to each node. If, for example, we were to think of nodes as web pages that we are browsing through following the links forever and ever. Another version of node centrality is betweenness centrality. And the way this is computed is by first figuring out which is the faster way to get from one node to the other, and then counting how many times we have to pass through the node we are looking at that specific moment. The last version I have here is the closeness centrality that, as the name suggests, quantifies how close our node is to all others. An important thing to note is that the concept of importance and centrality does not only apply to nodes but also to links, because in a network, links too will be more or less important. And to rank them, we can use betweenness centrality or the version of it for edges. And what we will end up with if we take a network like the map of Königsberg that we saw before, but including also the roads, is that the bridges in there, since they are scarce compared to the roads, will be more important because you'll pass through them a greater number of times, since you have not as many options. But let's move forward. Apart from the degree and the node centrality measures that we saw, there's another number that we can use to capture the behavior of the nodes and thus the entities they represent. This number is called the clustering coefficient and is based on the fact that, especially in social phenomena, the nodes show a tendency of organizing in groups that we will call communities. So this clustering coefficient basically tells us how tight the neighborhood of a node is, and as a result, how well connected our node is to the rest of the graph, or at least the ones around it. And the way this number is computed is by counting how many of a node use neighbors, let's say, are connected to each other compared to the total number of all possible couples of neighbors. And here I would like to dive a bit into sociology, because there's a concept, the one of zodiac closure, that is very close to what we just saw with the clustering coefficient. What the zodiac closure tells us is that if, let's say, Alice is friends with both Bob and Carol, then there will be a higher probability for Bob and Carol to make friends. And thus to close the triangle that is formed by Alice, Bob, and Carol. There are different explanations for this. First of all, we have that by sharing a common friend, Bob and Carol will be more likely to meet each other, but then they'll also be more likely to get along with each other. And on the other hand, we have the incentive that Alice has into introducing the two of them. So essentially what this suggests is that we look at the neighborhood of a node not from the point of view of the links, but in terms of triangles. And this is essentially the same thing, because the clustering coefficient can actually be reformulated as the number of closed triangles compared to the number of all triangles that are present in the neighborhood of the node we are looking at. And just to recap, you may see there's a filler here, because we first looked at degree, which is basically counting in how many couples of nodes that are connected to each other, the one we are interested in participates. And then we saw the clustering coefficient that can be reformulated in terms of open and closed triangles. Then you may ask, why not squares them? And this leads us directly to the concept of motifs or graphlets, that are basically tuples of nodes that are connected in a specific manner, and we can use as building blocks for networks. And of course, it's going to be more complex to count how many of a specific motif type, how many instances of a specific motif are present in the neighborhood of a node. And furthermore, as you can see in the picture here, there's quite a lot of combinations, even just with 6 nodes. But at the same time, the cost we are paying in the computational complexity is balanced by the fact that we'll most probably get some richer insights into the entities that we have in the network. And mentioning computational complexity, I would like to point out that some of these features are more at the level of the graph as a whole, while some others are more local. Of course, if we need the whole graph to compute a number, for example, that's the case with betweenness centrality, this is going to take quite a few time to compute. On the contrary, if we need just the nodes that are around the one we are interested in, this is going to be much faster. And this concept is known as shifting our focus from the whole graph to the ego graph of a node, that is its neighborhood, basically. And an example of this is counting motifs, which can be done only in the immediate neighborhood of a node, but also by taking into account the neighbors of the neighbors. And of course, the ego graph is going to be smaller, and as a result, the local variant of a feature is going to be faster to compute. But at the same time, since we don't have the full picture of what is going on in the network, we just can end up with less information. Before wrapping things up, I would like to make them a bit more practical with an example that most probably everyone is very familiar with, and that is the web, how to model it. So when it comes to the World Wide Web, we have a number of pages that we visit by following links that connect from one to the other. And as we did before for the bridges of Königsberg, we can map the pages to the nodes of a network and the hyperlinks to the edges of this network. The only difference here is that these edges will be directed, meaning that we can go from one point to the other, but not the other way around. And this is called a directed graph. This model of the web is the one on top of which the original algorithm developed by Google was built on. This algorithm, called PageRank, is based on the assumption that the importance of a page depends not only on the number of links pointing to it, but also on the importance of the sources of these links. It's pretty similar to eigenvector centrality. As a matter of fact, you can think of it as a specialized version that is adapted for directed networks, but there's another important difference to be made. And this is that PageRank allows us to, while browsing through pages, type an address in our address bar, press enter, and jump to another page that might be in a completely different part of the graph, regardless of whether it is connected or not from the one we come from. So what we end up having here is a model of the web pages that gives more importance to the ones that have many incoming links and few outgoing ones compared to those pages that are linked to by few but linked to many. And it also gives the possibility for the user to jump from one point to the other. And then, like eigenvector centrality, we basically end up with a number that tells us what is our probability of ending up in a given page if we were to browse forever and ever. And this probability is the one according to which the web pages are ranked. And that's it. Here are a few references and contacts. And just to sum it up, what we saw today is that there's a variety of measures that we can use to assess who is more important than who in a social network, for example. And all these features have pros and cons. It's mostly a matter of finding a balance between expressiveness and performance. But I would like to conclude by saying that we looked at a very tiny part of what can be done with graphs, and I hope that you got a glimpse of how versatile and pervasive they are as a data structure and why it's very cool to work with them.